Hi, welcome to our ninth lecture, ruthenium-catalyzed hydroxylation of unreactive tertiary centers. Oxidative functionalization of alkanes, either directly with oxygen or other oxidizing reagents into functionalized organic molecules, is of great interest in industry. Such functionalization of alkanes generally requires heterogeneous reactions, high temperatures and pressures, and occur without great selectivity. In addition, processes that rely on transition metal complexes to mediate CH oxidation often are limited due to undesired reaction pathways, such as oxidative ligand degradation and/or catalytic multimerization. Ruthenium tetroxide can be generated in catalytic quantities from ruthenium trichloride. Ruthenium tetroxide is a potent oxidant that does not require any ligands. However, in stoichiometric amounts, ruthenium tetroxide can react with pi systems, other saturated CH bonds, and aromatic rings. For this purpose, a selective catalytic process under milder conditions is desirable, especially in the case of more complex molecules. Here, we have a bridged tricyclic alkane with a siddrain skeleton. These are of interest in the perfume industry. The bridged tricyclic siddrain skeleton features 4 tertiary CH bonds. The ruthenium-catalyzed oxidation of siddrain occurs stereoselectivity under mild conditions at the less hindered tertiary positions. Here we see siddrain was directly oxidized at room temperature to epidsiderol at 69% yield. Dry ozonation techniques led to overoxidation to the diol in 18% yield at the 2 less sterically hindered tertiary carbons. Bois was able to optimize these conditions to generate ruthenium tetroxide in situ in catalytic amounts from ruthenium trichloride, KBrO3, water, pyridine, acetonitrile at 60 degrees. Acetonitrile, when he screened, was the optimal solvent, and KBrO3 was the optimal oxidant. He did find that by adding 10 mol% of pyridine, the yield was significantly increased. We know that with osmium tetroxide oxidations, pyridine assists in increasing the yield. Here in example 1 is a real live molecule from industry in which we applied Bois conditions and obtained the desired tertiary alcohol in 62% yield. However, when we went to the pyridine system in example 2, we repeated the reaction conditions and only obtained 15% yield. Detailed kinetic and computational studies give weight to the mechanism. It involves a concerted asynchronous 3+2 cycloaddition between ruthenium tetroxide and the substrate CH bond. Accordingly, such a process makes the stereoselective hydroxylation of optically active tertiary CH centers. This is a desirable feature for this hydroxylation method. However, there were questions surrounding the scope. The primary concern is the perception that ruthenium tetroxide is a powerful non-selective oxidant. To perform the hydroxylation on the tertiary center of a pyridine substrate, we went ahead and used the Fuchs method with Corey modification that relied on rhenium and peroxide. To our delight, we were able to get the desired product in 84% yield. However, when we turned to a benzylic substrate, only a trace of product was observed. And this should be an alcohol here. I'll just kind of draw that in. H. That's supposed to be an H. Only a trace of desired product was observed. So here are some conditions which you could do to get around this, is you could probably go through a Grignard reaction, add an allylic group, and then oxidize it up to the desired diacid. And in fact, that's what we ended up doing to get these other sorts of molecules. However, that does not deal with the activation at the tertiary center, therefore it's not discussed in this lecture, but it is how we got to the desired product.